This video is on Descartes' rule of signs and the rational root theorem. We're going to start with Descartes' rule of signs. Now, the reason that we're going to use this is to help determine the number of real roots and the nature of them. So whether there will be so many positive and so many negative roots to a polynomial equation. We're going to count the number of sign changes. Now, they have to be in descending order, standard form, for you to do that. That's going to be the maximum number of positive roots. Don't worry, we'll do an example and this will make more sense. So what you're doing is in blue, and sort of an explanation of it is in parentheses in black. You should copy this down, but leave room after it for a couple of examples on the next screen. You should pause the video to get this part into your notes. So let's look at our first example. In this first one, we see that we have descending order already there. So once it's in descending order, we're going to look and count the number of sign changes, including the first one. So the first term is positive, but since the second term is negative, we're looking at one sign change here. And then from the second term to the third term, we have another sign change. So there's two sign changes in this polynomial. That means that there will be less than or equal to 2 positive real roots. Remember, roots are solutions or x-intercepts or zeros. They're all referring to the same thing. Now, here's the trick. For negative roots, to know how many there are, we need to replace the x with a negative x and see how that might change the sign of each term. So what I generally do, above or below, it doesn't matter, is write what the new sign will be. If I replace x with negative x, a negative number to the power of 6 will still result in a positive answer. And you could use it you could check it just by using a negative 1 to the power of 6. Be careful, you have to put the negative 1 in parentheses to the power of 6 outside the parentheses. Otherwise, it won't give you the right signed answer. So this will become, or stay actually, positive. Here, if I replace the x with a negative x squared becomes positive, and multiplied to this negative already here, we're staying negative. All right, look what happens here. When I replace x with negative x, this becomes minus 5x. Because this is 5 times x. So 5 times negative x would be negative 5x. So the sign actually changes when your exponent is an odd number. That's going to be the result. And you can check it just by using a negative 1 in place of the x. Again, we're looking for sign changes, and there's only one this time because going from negative to a negative isn't a change. So we will have less than or equal to 1 negative real root. Now I say real because the alternative is that there could be complex roots. And since we have at most 2 positive real roots and at most 1 negative real root, we're still only looking maximum 3 roots that we could find. But since this has a degree of 6, unless there's lots of repeats here, this is all we're going to get. The others would have to be complex. All right, let's look. The goal here is going to be to factor these kinds of things. We'll do that in a moment. I'd like you to try to use Descartes' rule of signs to figure out what the maximum number of positive and negative roots are for this next example. Pause the video and try it now. Okay, how'd you do? I see one sign change the way the signs are here, and so there's less than or equal to 1 positive real root. Remember, anywhere there's an odd exponent, the sign for that term is going to change. So this is staying negative. This, because of the odd exponent, will turn positive. This stays positive, and this one, remember, the 1 for the exponent is an odd number, and so this changes to negative instead of positive. My sign changes, there's 2 of them. Positive to positive is no change. So I have 2 negative real roots at most. All right, now let's learn what we're going to do. We're going to use the rational root theorem together with Descartes' rule of signs to find the factored form of this polynomial. To do that, we're going to check with Descartes' rule of signs first and decide the maximum number of positive and negative roots. I see one sign change right here, so that's going to be less than or equal to 1 positive real root. So that means there's either none or there's 1 positive root. Now if I replace these with a negative x, this will turn negative, this will stay positive, this will turn positive, it changes signs when there's a negative exponent, and this will be negative. I have 2 sign changes, so that's less than or equal to 2 negative real roots. This is good because once I know that I found, let's say, 1 positive root, I can stop looking at other positive possibilities. The possibilities are going to come from the factors of the constant term, which in this case is -8, over the factors of the leading coefficient, which in this case is 3. And this is exactly what the rational root theorem is telling us. All possible roots, that doesn't mean they're roots, it means that that's the new pool of possibilities, are all the positive and negative combinations of factors of the constant term divided by the factors of the leading coefficient. Here's what this means. We take the -8, we list out all of the factors. So positive and negative, 1 times 8, so positive and -1, positive and -8. 2 times 4 is also 8, so positive and -2, positive and -4. Those are all the factors of 8. Below that, we're going to put the leading coefficient and list out all of its factors. I have positive and -1 and positive and -3. You always do the positive and negative versions. So your total pool of possibilities is going to include everything in the first row, so all of those, and remember what it said, divided by the factors of the leading coefficient. I used all of those because any of those over 1 will give me all of those again. But all of these also have to go over 3. So 1 over 3. So positive and -1/3. 8 over 3. So positive or -8/3. 2 over 3. Positive and -2/3. And 4 over 3. Positive and -4/3. These are all the possibilities. Now there's a lot of them, but I do have some advice for you. And my best advice is to try the easy numbers first. Try positive and -1. Try positive and -2. I don't have a 3 here, but I could try 4 if 1 and 2 don't give me all the answers I need. Here's what we're going to do. We're going to use synthetic division. We're going to try dividing using a 1 outside the L bracket. My coefficients are 3, 8, -3, and -8. If you do the synthetic division, if -1, which is the opposite of this, is a factor, x minus 1 is a factor of this, then this should give me a remainder of 0. So we're going to take a look. If we bring down the 3, 1 times 3 is 3. We add down. We multiply this times the 1 again. There's the 11. We add down. We multiply times the 1 again, and we add down. And look, we get a remainder of 0. That means that this works. It means that one of the solutions is x equals 1. And if a solution is x equals 1, the factor is x minus 1, right? Because it's the opposite. And so we have found one of the factors of this polynomial. Sometimes it takes a few tries. If one number doesn't work, cross it out, try a -1. If that doesn't work, cross it out, try a 2 or a -2. You're going to do the best you can, but a lot of times 1s and 2s work, so always try them first. Remember, if you don't get a remainder of 0, cross it out. It means that that number you picked out here is not going to produce a factor. Once you get down to 3 numbers, you have a quadratic. And it's easier to factor that quadratic than it is to keep checking with using synthetic division. Remember, those 3 numbers, we can put x back in. 3x squared plus 11x plus 8. The 0 was a remainder, so we don't need that. We can then factor this, and you need to use the box or pants. The leading coefficient is 3, so you cannot use the shortcut here. Go ahead and pause the video and factor that quadratic, and then I'll tell you where we go from there. All right, I hope you factored that correctly. Yours might have had the x plus 1 first, and that's okay. So what we end up with is 3 sets of parentheses. This first one that we found using synthetic division, the 3x plus 8, and the x plus 1. This is factored form of our original polynomial. It is what f of x is equal to. This is standard form, this is factored form, and that's our goal. Save yourself a lot of time by factoring the quadratic. Once you get down to 3 numbers before the 0, go ahead and write them with the x terms and then factor it. I'd like for my honors students to try this problem, and then we'll check it in class together. There's some different things that are going to happen here, so I'll warn you to look out for something unusual, and then we'll talk about it in class. Remember to use Descartes' rule of sign first, so you know how many solutions there will be and whether they're positive or negative. Use synthetic division as many times as necessary to apply the theorem. Sometimes it takes a few tries. We have filled entire pages of synthetic division to solve some of these problems. Don't get discouraged. You'll find the answers. Be very careful with your signs. Once you're down to a quadratic equation, 3 numbers left at the bottom before the 0 remainder at the bottom of synthetic division, just write those with the x's back in. The first number x squared plus the second number x plus the constant, and factored the quadratic to find the last 2 solutions. You don't have to keep doing synthetic division and guessing what divides in, although you can if you want to.